today's lecture, we are going to discuss about sample and hold circuit. It's a great interesting topic, right? So what is meant by sample and hold circuit? First, let us discuss what is sampling. What is meant by sampling? Just taking samples, right? So see, if I have an analog signal, this is an analog signal which in general we call it as a continuous time signal. If you consider a continuous time signal, we can have infinite number of samples, right? We can have infinite number of samples, or we can say as infinite time instance, right? Infinite time instances. Instead of processing these infinite time instances by the digital systems becomes complex. And so what happens is, we'll be taking samples out of the signal and then these samples will be given to a digital system for further processing. Okay, so taking samples from this is known as sampling. Simply we can tell, we have blood flowing in our body, and if we want to test the group of the blood, then what they are doing, we are just taking a blood sample, and after checking it, after doing all the processing, we are telling the whole blood is this group, so and so group, right? Similarly, the same is the case here too. What we will be doing is, instead of taking infinite number of points for processing, it becomes a tedious task. So what happens is, we will be taking samples and these samples will be processed. Okay, and that process is known as sample. The device which is used for performing sampling is known as sampler. Okay, sampler. So what happens if I send an analog signal to a sampler? It will take sample output. That is, I will not be having a continuous signal like this. Instead, I will be having samples at specific time instances. Right? These are samples. I don't have any continuous signal. See, I have the output at 0, output at 1 second, 2 second, 3 second, 4, 5, 6, 7. Right? So now I have only the same signal, but I have only 7 samples. I can sample these 7, process these 7 samples, and we can have an inference that the output of this signal will be same as that of this signal. So for that we use the sampler. How the sampler will use, right? So just see, if I have a switch like this. If I have a switch like this is the input signal, this one. If I have a switch like this, then the switch itself can act as a sampler, is it not? Right? See, if I have, this is a signal which is entering here, and whenever the switch is closing, I will be getting the output. Whenever the switch is open, no output, 0 output. Whenever the switch is closed, we will be getting the output. Whenever the switch is open, no output. Right? So simply a switch can act as a sampler. Okay? So another question comes into our mind. How long I should close the switch and how long should I keep the switch open? That is the question. See, this sampling instances should be same, or else we will not get a good output for this signal, right? So the instances has to be maintained equal. For that we have a theorem known as sampling theorem. Sampling theorem. What does this theorem states? It states that Fs is greater than or equal to 2Fm. Fs is greater than or equal to 2Fm. Fm is the maximum frequency of the signal, and Fs is the sample signal. Right? See, the sample signal's frequency should be greater than or equal to twice that of the maximum frequency of the signal. So what is the minimum condition here? Should be at least 2Fm, which is the minimum condition, and this is known as the Nyquist rate. Nyquist rate. That is the minimum frequency at which the signal has to be sampled, is known as the Nyquist rate. Okay. So this is sampling theorem and this is the Nyquist rate. So if I want a good output, the output of the sample signal, if it should be perfect, then the sampling theorem This is sample frequency of the sample signal, and this is the maximum frequency of the input signal. Right? At least this Nyquist rate should be followed. What happens if I do not follow the sampling theorem? See, once after sampling, if you see the spectrum, right? The spectrum should be a good one. This is how the spectrum looks like. Okay? If you see here, if it is equal to 2 FM, then the spectrum looks like this. Okay? This is for every single cycle of the signal, and it looks like this. Exactly the end touches. Suppose if it is a oversample signal, what happens is it overlaps. Right? So we will be losing the signals at this point. So if it is undersampled, then what happens? The space will be very high. So we lose the bandwidth. Right? So it should not be oversampled, or we should not undersample. So exactly the frequency should be maintained. This is known as sampling frequency. So when we are closing and opening the switch, that is the time instance, TS, let us consider. This opening and closing the switch should follow the sampling theorem, Fs. Okay. Now, so we have discussed about this continuous time signal or analog signal, and now this becomes discrete signal. Okay, this becomes discrete. That is, it is digital with respect to time. There is no intermittent values, either a low or a high. 0, 1, 2, either a low or a high, either a low or a high. No intermittent values. So in this time, with respect to time, it is discrete, right? Digital, but with respect to amplitude it is not so, right? If it is with respect to amplitude also, if it is digital, then only we call the signal as a digital signal on a whole. Now this has to be maintained. This amplitude as well as time should be digital in nature. Okay? So for that we will be having a quantization circuit. Right? This quantization circuit, for this quantization circuit, in order to maintain after the sampler, we will be having a quantizer. We will be having a quantizer. So, this output of this quantizer, so in order to maintain this quantizer, in order to make the quantizer to work properly, we need to give constant input to the quantizer, and so that is maintained by this hold circuit, which is just a capacitor, which is a storage device. Okay, so this output will be held up by the capacitor in order to give it to the quantizer, and the quantizer will give. So now see, we will not be having an intermittent value. Here also we will be having either 0, 1, 2 and so on. Exactly a digital signal. Okay, so once after sampling, we will be getting a discrete signal which is partially digital, and after quantization we will be getting an exactly digital signal. Okay, so from analog to convert digital, we have a sample and hold circuit. A simple switch along with a capacitor can act as a sample and hold circuit, and in order to get a good result, the sampling theorem and Nyquist, at least Nyquist rate, should be followed. Thank you.